Hi, we're going to talk about chapter 6. We're only going to talk about the first 6 sections. The rest of it's interesting. It's descriptive chemistry about the different groups of the periodic table and some of their chemical properties. So you might want to read it out of interest, but I'm not going to hold you accountable for it. So let me first share. You should have the periodic table out, the one that I gave you that you'll be able to bring to tests, because while we go through this, you can put the trends on the periodic table, and that will help you understand them and remember them. There'll also be times when we look at different elements and their properties, and it's good to be able to look at the periodic table and know where they are. So when we think about electron configurations in chapter 5, we learned about electron configurations for atoms. And now in this chapter, we're going to think about some of the trends. So it's a trend you should have on your periodic table already, that group 1. So the alkali metals, they like to form +1 cations. And when you look at their electron configurations, it will make sense to you. So neutral sodium atom on the left-hand side has 1s2, 2s2, 2p6, 3s1. So it essentially has that full inert gas of neon, and then it has a 3s1, one extra electron outside that filled shell. And so that electron, the valence electron, is easy to pull off. And when you make sodium into the +1 cation, you essentially end up with just neon, 1s2, 2s2, 2p6. And so that's a very stable configuration. And if you look at lithium, potassium, all of those in that group, they'll have a similar situation, whereas the neutral atom, it's a noble gas plus 1 extra electron. And then when you make it into a cation, it's just that noble gas configuration. And we know that that's a very stable configuration. So the same thing's true when you look at the far right-hand side of the periodic table. All the halogens like to be -1. And if you look at their electron configurations, you start out with an almost full electron configuration. So you almost look like argon, but you're 1 electron short. So if you add 1 electron to a neutral chlorine atom, you end up with argon. And so you go from a partially filled shell to a completely filled shell. So one of the things you'll notice really quickly is that when things can look like a noble gas configuration, they're going to be more stable. So you can see the same exact thing happen. So group 1, where sodium is, you add you take off an electron and you get a noble gas. Group 2, you take off 2 electrons and you get a noble gas. So group 2 elements like to be +2. And that's just showing what we just talked about. When you're on the far right, you're going to be more likely to add electrons. So the non-metals on the far right can add electrons easier to become noble gases, because if you tried to take them off and make them cations, you'd have to take off so many that it would take way too much energy. So group 6A and 7A can add 2 electrons or 1 electron and become like noble gas configurations. So this just gives you some common main group ions and their noble gas electron configurations. So group 1, +1, group 2, +2, group 3 tends to be +3, 6A, -2, 7A, -1. And in each case, it shows you then that their electron configuration looks like one of the stable, very inert atoms from group 8A. So there are a couple exceptions when you think about how you look at an electron configuration for an ion. And the important one we'll talk about is when you're in the transition metals. So if we have something like iron and you were to make the electron configuration as we did in chapter 5, it would have a filled argon shell, and then it would have 2 electrons in the S4s, and then you'd have 6 electrons in the 3D. When you make those transition metals into ions, always cations, you're going to take the electrons first out of the s orbital. So even though the d filled second, the electrons will come out of the s. So when you look at it, in the first case, it's showing you iron becoming oxidation state of 2+, and so you had to take out the 2 electrons in the s orbital. And when it becomes a 3+, you have to take out those 2 electrons from the s orbital, and then also 1 from one of the d. So after you get them all out of the s, you can start taking them out of the d. So the reason this happens is, when you think about it, when you have a neutral iron atom, it has an equal number of protons and electrons. But once you start taking electrons out, you have more protons than electrons. And so that shifts the energy of those different orbitals, the s and the d, and it makes it so that the s orbital is actually higher in energy than the d. And so you're going to take them out of the higher energy orbital. So ions will have trends in their radii just like atoms did. So the atoms, the trend that you probably already have on your periodic table, hopefully, is as you go down a group, they get bigger, but as you go from left to right, they get smaller. When you look at the size for cations and anions, it's going to make a ton of sense that cations are always smaller than the neutral atom that they're made from. And that just makes total sense because you're taking electrons out of the valence shell. And so the Z effective becomes larger. The electrons that are in the inner shell see the nucleus and are held tighter. And so just with, in the left-hand side, 1 less electron, the cations in purple are always smaller than the blue neutral atoms. And then if you were to make a 2+ out of the group 2 metals, you'll find that they're even smaller than the neutral atoms that they were created from. So it didn't make sense that the opposite is true for making anions. So if you have a neutral atom and you add an extra electron, but you haven't added a proton, then the Z effective is smaller. That electron doesn't see as much charge. And so anions are larger than their neutral atoms because of the decrease in effective nuclear charge. And also because if you think about it, you're putting that last electron in these halogen examples into an orbital that already has an electron in it. So you have electron-electron repulsion, and you have a decrease in Z effective. So ions that are negative anions are going to be bigger than the neutral atoms they were made from. So another trend you can see in the periodic table, which is related to the size of atoms, is the ionization energy. So the ionization energy, EI, is the amount of energy necessary to remove the highest energy electron from an isolated neutral atom in the gas state. So if we have a hydrogen atom, you can go back and look at how much lower in energy it is when that electron is attached to the proton. You'd have to put that much energy in to pull it off so that you'd have just the proton and the electron separated from each other. So that's the ionization energy. So here are the trends. In ionization energy, let's think, yeah. So the trend is pretty much just related to the trend in size. So if something is bigger, then it's going to be easier to take an electron off because it doesn't see the nucleus as clearly. So something really small like helium, it's the smallest atom. The electron is held really close, and so it's going to be hard to pull it off. Whereas when you get way over to radon, it has the same outer shell electron configuration, but the electrons are much further away from the nucleus, so it's going to be easier. And then as you think about going across the period, you're going to have little glitches, but it tends to be that as you go from left to right, the ionization energy goes up, because as we know, when you go left to right on the periodic table, the atoms are shrinking. But you see little glitches, and those little glitches have to do with the electron configuration. So for example, lithium to beryllium to boron. So boron has a higher or higher ionization energy than boron. And that is, I think in the next slide it describes, yeah, because it has a smaller effective nuclear charge. So it has a smaller effective nuclear charge when you get to boron. So think about beryllium. Beryllium has 2 electrons in the s orbital, and then the electron for boron goes into a p orbital. And s electrons are closer to the nucleus on average. So that means that the boron's electron, the 3rd electron, is shielded more from the nucleus. And so there's a smaller effective nuclear charge. So it's going to be easier to pull off the electron on boron than beryllium. So the trend is generally from left to right, the ionization energy goes up, but you have little glitches like that where it goes down. From nitrogen to oxygen, so when you're at nitrogen, and this trend is the same in each of the periods, like from phosphorus to sulfur, we can talk about them in the same way. So when you're at nitrogen, you have 3 p orbitals, 1 electron when you made boron, 1 electron when you made carbon, 1 when you made nitrogen, all going into single p orbitals. But then the oxygen has 1 paired, a set of paired electrons in one of the p orbitals. So electrons in the same orbital repel each other. So it's going to be slightly easier to take an electron out of oxygen because you're going to be taking it out of a orbital that has 2 electrons, and that electron-electron repulsion is essentially helping you pull that out because it's not as happy there as if it was in a single orbital all by itself. So that's what I just talked about. And so you can talk about the first ionization energy, which we're talking about here, taking off the highest energy electron 1, but you can also talk about higher ionization energies. So the first equation shows you the first ionization energy process. And then once you've taken an electron off, then you can take the metal plus and add some more energy and take another electron off. And then you could take the second, or the doubly charged cation and take another electron off. And so when you look at this table, it's giving you the trends in higher electron or ionization energies. And what you'll notice here, they don't talk about it, but the important thing is that there's always going to be places where there are huge differences in the ionization energy. So yeah, so if you think about sodium, for example, the second ionization energy for sodium is really high. And that's because if you're taking the second electron off of sodium, you have a filled neon shell. And so it's going to take a lot of energy to take that electron off. So you're going to see differences like that when you look at the periodic table. So whereas when you're looking at magnesium, its second ionization energy isn't nearly as high as sodium because you're taking off the second electron out of a 3s orbital. So you're not going into an inner shell when you take off the second electron from magnesium. So that zigzag line essentially is showing you when you're having to dip into an inner shell and when it's going to take a lot more energy to pull off an electron. So we'll do some problems where we look at those relative values and make sense out of why there's huge differences in some of the higher ionization energies. Electron affinity is the energy change that occurs when an electron is added to an isolated atom in the gaseous state. So now you're going to be making an anion. And this shows you that the halogens give off a lot more energy when you attach an electron. So that means it's a much more favorable situation because this is negative going up, which means more energy is released, which means it's a more favorable process. Whereas if you look at the bottom where it's 0, that's the noble gases, where it's impossible to add an electron to them essentially. And so their electron affinity is 0. And so if we look at all of these things we've talked about in this first 6 sections of chapter 6, you can summarize them all with the octet rule, which says main group elements tend to undergo reactions that leave them with 8 outer shell electrons. That is, main group elements react so that they attain a noble gas electron configuration with filled S and P sublevels in their valence electron shells. So that's how we can explain why group 1 likes to be +1s, why the halogens like to be -1. All of it can be explained by just thinking about each of them then has a filled S and P outer shell and our outer subshells, and then they have electron configurations like the noble gases. So metals tend to have low ionization energies and low electron affinities. They tend to lose 1 or more electrons, whereas non-metals tend to have high electron ionization or ionization energies. It's hard to pull an electron off, but high electron affinities, which means it's easy to stick an electron on. So they tend to gain 1 or more electrons. And this is the only thing we'll talk about with the formation of ionic solids. The section on forming an ionic solid really goes better with chapter 8 when we're talking about energy released in reactions. And so I just wanted to talk a little bit about this. So we've drawn the electron configurations for sodium and chloride. Our sodium and chlorine, when they form a cation and an anion. So when they're neutral atoms, they have unfilled outer shells. Sodium can become Na plus by giving up an electron, and then it has the filled shell of neon. And then chlorine, if it picks up an electron, can look like argon. Yeah. And so that process of exchanging the electron may or may not take energy. So it depends on the relative ionization energy of sodium and the electron affinity of chlorine. But once those are formed, the ionic bond is then formed because the positive sodium and the negative chlorine are held together just by that electrostatic force, which is fairly strong. So you make the ions, and then an ionic bond is the fact that something positive and something negative are attracted to each other. So the rest of the chapter will come back to the formation of solids when we look at thermochemistry, and the rest of the descriptive chemistry we won't cover. You can read it, it's interesting. We might look at some of the reactions as demos, but I won't hold you accountable for it. So we will go on to chapter 7 next.